Okay, good morning, afternoon, or evening, everybody. Welcome to the NASA Commercial SmallSat Data Acquisition Program Vendor Focus Spire webinar. This is your host, Jennifer Brennan. It is 11 a.m. Eastern Time, so what I'd like to do is get started here. What I'll do first is begin today's webinar with a few logistics. To ensure the best audio experience, all participants have been placed in silent mode, but if you have any issues or questions, please enter them into the Q&A panel rather than the chat, and you should see that located in the panel on the right side of your screen. If you don't see that, then click on the three dots in the bottom right corner of your screen, and that will pull up your panel options. Then you can insert a check mark next to the Q&A panel. Today's webinar is being recorded. The recording will be posted to the Commercial SmallSat Data Acquisition Program playlist within our NASA Earth Data YouTube channel within a week of completion. Once completed, what I will do is I will send an email to all registrants and participants that includes both the links to the presentation slide decks used within today's webinar, as well as the recording link. As far as timing is concerned, today's webinar will be 1 hour long with 45 to 50 minutes allocated to the presentation and live demonstrations. A 15-minute Q&A period will follow, and depending on the volume of questions we receive, we may extend the Q&A session an additional 15 minutes from end time, but we will have a hard cutoff of 12:15 p.m. Eastern. During this afternoon's webinar, we will have one speaker from NASA's Commercial SmallSat Data Acquisition Program and 3 speakers from Spire to present the vendor content. I'm actually going to switch over here to the next slide. Excuse me. Dana Ostrenga will be our first speaker. She is the NASA Commercial SmallSat Data Acquisition Project Manager here at Goddard Space Flight Center. She will kick us off with an introduction to the CSDA mission and program goals and provide an overview of the CSDA IDIQ contract process. From there, we will transition to our Spire speakers. Our 3 speakers from Spire are Chris Lindner. Chris is an executive from Spire, an account executive from Spire Federal. He will begin today's webinar with an introduction to Spire, its suite of satellites and core data product suite. From there, we will transition over to our second speaker, Vu Nguyen, who is the technical director for Spire's GNSS-RO Pro products. Once Vu has finished with this presentation, we'll then toss it over to our third speaker from Spire, Philip Jales. Philip will provide an introduction to the GNSS-R constellation, its data products and data processing, and the primary applications from these products. And Philip is the technical director for GNSS-R products. Finally, we will actually then toss it back over to Chris to wrap out the Spire portion of today's webinar with information about Spire's non-CSDA products and capabilities. And then we will open up our optional final polls and proceed directly to the question and answer session. So before I toss it over to Dana, just a few points about the Q&A session this afternoon. We will try to answer all questions within the time allotted, but if we're not able to address your question during the Q&A, our speakers will be able to follow up with you offline. And then with that, it is my pleasure to introduce today's first speaker, Dana Ostrenga. Dana, so with that, let me stop sharing my screen, and I am going to toss the presenter role over to you, Dana. All right, perfect. Okay, Dana, I can see your screen. We do not have audio quite yet.
Thank you. Got to unmute myself. So thanks, Jennifer, for getting us started today. Welcome again all to the Commercial SmallSat Data Acquisition Program webinar series. We're going to be here today to learn about Spire. I am Dana Ostrenga, the CSDA Project Manager at NASA Goddard Space Flight Center. So if you've missed any of our previous webinars, just to give you a little background about our program, the Commercial SmallSat Data Acquisition Program, or CSDA, we have a mission to focus on identifying, evaluating, and acquiring commercial satellite data that supports NASA's Earth science, research, and application goals. So the program has 5 main elements. 1, to establish a continuous and repeatable process to on-ramp new commercial data vendors. to enable sustained use of that data for broader dissemination to our scientific community, to ensure long-term data preservation, access, and distribution of that data, ensuring scientific reproducibility, and to collaborate and partner with interagency and international partners on the evaluation and scientific use of the data acquired, and then to comply with the 2003 U.S. commercial remote sensing policy. I don't know why it's not going. Okay, so we recently completed our IDIQ on Ramp 1 back in September. This was a multiple award on an indefinite delivery, indefinite quantity fixed price contract that was in response to an RFP that closed March 25th, 2024. The contract goes through November 15th, 2028, and we have awarded 8 new vendors under this new IDIQ on Ramp 1, which includes Black Sky, ISci, MDA, Pixel, Planet, Satellogic, Paladin Brown, and the Tomorrow Company. These 8 new vendors joined our previously awarded 7 vendors, which include Spire, and this means that through the CSDA program, we will evaluate their data, and once complete with evaluation, they'll be able to propose to competitive task orders. If they are previous vendors like Spire that have held either a blanket purchase agreement or what we call a BPA contract, then they've already been evaluated and they can now compete under the IDIQ. Spire has been one of our vendors that have been a part of the program since it was started as a pilot in 2019. The program did an assessment of the radio occultation after awarding Spire a BPA contract. Spire has entered the IDIQ contract initially in October 2023. And Spire was awarded a 12-month task order on August 12th of this year to provide continuous radio occultation data to the program. There is an existing USG EULA for use, and you can see the suite of data the program has acquired listed here. Spire will dive a little deeper into those individual product suite in a few moments. If you qualify for access, you can get authorization through the CSDA web form that's listed, and you can see here a screenshot and a link of our SmallSat Data Explorer where you can search and access data as an approved user. Data that's downloaded will continue to be integrated and available through this interface, and then it's also being added to the Earth Data Search client so that it can be searchable alongside NASA-supported mission and project data. On the CSDA website, we do currently have a listing of all of our current data holdings that goes above and beyond. Spire includes all of our sensor data. The date range of the data is available, and you can see how you can get access to the individual data products. We also list any associated EULA with that data. We do try to keep this updated, and we will be revising the site in the future to make the data information a little bit more robust so you know specifics on each of these products and sensors. Once again, this can be accessed through the CSDA website, and the links will be available in the slides that will be made available to all the registrants after the webinar. So that brings us to the next portion of our webinar. Please welcome our invited speakers, Chris Lindner, Vu Nguyen, and Philip Jales, who will talk to you more about Spire. And I'll stop presenting, and Chris, you can take it away.
Hey, thanks a lot, Dana. I'll get the video turned on as well as get my slides shared quickly as well. Let's see. All right. Well, first of all, thank you, Dana, for the intros, and thank you to you and Jennifer, CSDA team, and NASA for hosting this webinar and really providing this opportunity for us to discuss Spire's contributions to the CSDA program, as well as what we're doing outside of the program. Also like to thank our audience members. Those of you tuning into this webinar have no idea how many there are or where you're watching from, but we're excited to be here, and I hope that we can provide a good overview of what Spire is doing and answer any questions you all may have. So with that, we'll go ahead and get into it. All right, so Spire is a Cube satellite-powered remote sensing company. We're headquartered out of our DC area office in Tysons Corner, Virginia, with around 450 or so employees. These employees are spread out all over the globe in the US. In addition to our DC office, we have offices in Boulder, Colorado, as well as San Francisco. And outside of the US, we have wholly owned subsidiaries in Canada, the UK, Germany, Luxembourg, and Singapore. I work out of our DC office. Vu and Troy are out of Boulder, and Phil is out of our UK area. Spire is vertically integrated, meaning that we do everything when it comes to satellites except for the launch itself. We design, test, and build our own satellites, as well as perform the on-orbit operations and management of our constellation. For the launches, we'll usually contract with SpaceX, so pretty much every transporter mission that goes up will have several Spire satellites on it. And as you can see from the bottom here, our core data products include maritime, aviation, weather, and Earth intelligence applications. And we're also able to offer what we call Spire Space Services, which is where we'll host customer payloads on our satellites. And I will get into all of those in a more detail a little bit later on. As far as our constellation goes, it's the largest multi-purpose constellation in the world. We've launched over 180 satellites into low Earth orbit to date, including 7 on the most recent Transporter 11 mission in August. Our satellites have almost 700 years of cumulative flight heritage and primarily host software-defined radios that collect RF signals and transform them into near real-time suite of commercial data products that I mentioned on the last slide. Spire also owns and operates a global network of over 34 ground stations and antenna systems with various combinations of UHF, S, and X-band communications capabilities. And our approach is really to collect and demodulate signals on board the satellite and then transmit our data to our ground stations, where that data remains encrypted until it arrives at our US-based cloud computing installations, where it is then cleaned, enriched, and transformed into our user-facing APIs for dissemination. This chart here is an overview of all of Spire's capabilities for reference. I will get into all of these shortly, but just the blue is what is currently offered through the CSDA program, and then the green are capabilities outside of CSDA. And I'll just pause here for a few seconds to give everyone a brief opportunity to look at this, but these slides will be available after this webinar if you need to go back and reference this slide. All right, and then moving on to our Earth intelligence constellation, we have over 20 satellites currently in orbit that are using a variety of techniques to collect atmospheric, weather, and Earth observation data points. These satellites utilize a 3U form factor, which is our smallest satellite and about the size of a loaf of bread. We're collecting signals from GNSS constellations and using the techniques of radio occultation and reflectometry. Radio occultation provides atmospheric measurements such as temperature, pressure, and humidity, as well as ionospheric measurements such as total electron content, scintillation indices, and electron density profiles. Our reflectometry satellites utilize 2 different methods, the first being grazing angle to provide insights into sea ice, like surface area and thickness, and then the second being Near-Nadir reflectometry to measure ocean roughness and derive ocean winds in addition to soil moisture measurements. The last point I'll make on this slide is next year's launch of our hyperspectral microwave sounder. It'll provide next generation atmospheric observations, and I'll touch more on that on a later slide. So, but with that, I'll turn it over to Vu to dive deeper into radio occultation.
Thanks, Chris. Hi, everyone. So I'll now summarize Spire's GNSS-RO collection capabilities and data product suite. So for those of you who are unfamiliar with the RO technique, this technique utilizes phase measurements of the GNSS signal as it passes through the Earth's atmosphere. The amount of phase delay can be converted into a Benny angle, which is sensitive to atmospheric properties such as temperature and water vapor, with benefits to operational numerical weather prediction. These GNSS signals are collected with our in-house built Stratus receiver, which was first built in 2017. This receiver has the ability to track all major GNSS constellations at dual frequencies in open loop tracking mode. Along the way, the Stratus receiver has demonstrated many firsts in the RO technology space, including the first to produce high-quality profiles from a miniaturized CubeSat platform. The picture on the lower left shows an example of what our LEMUR platform with GNSS-RO capabilities looks like in orbit right now. You can see that on the side of the spacecraft, we have 1 or 2 RO antennas pointing towards the Earth's limb in order to collect the occulted GNSS signals for atmospheric property derivation. The antenna on the top of the spacecraft is a one-patch antenna that has a wide field of view designed to track multiple simultaneous GNSS signals as possible. The schematic on the right shows our current measurement configuration. If you start at the bottom, you can see that we begin tracking of high rate 50 hertz data of the Earth's atmosphere at 170 kilometers, and we track that high rate data all the way to below the surface of the Earth. At higher elevation angles, we also track 1 hertz signals in closed loop. This is mainly intended for precise orbit determination of our receiver, but they can also be used for ionospheric derivation of total electron content. Next slide, please. This slide here summarizes our RO production over the time frame of the NASA CSDA. So the plot on the lower left here shows an example, shows the production of our RO daily production from 2019 to present. You can see that in 2019, we were producing below 5,000 radio occultation profiles per day. That quickly ramped up to around 20,000 RO profiles per day. To put that into context, that is about 4 times the amount of the Cosmic 2 constellation. The plots on the right show an example of what our daily spatial coverage looks like in 2022. So you can see on the upper right, this shows what our spatial coverage is over the globe over one day, where each blue dot represents the location of each radio occultation profile. We can collect, of course, all latitude and longitude grid boxes over the course of a day. The plot on the bottom shows a latitude local time plot. You can see that due to the diverse set of orbits that our satellites are situated in, we can collect multiple measurements at multiple local time hours. Next slide. So these data are collected by our spacecraft and then downloaded or downlinked to the ground using our custom ground station network. And then from there, they are processed into all data levels using our state-of-the-art retrieval processing system. We make available through the NASA CSDA all data levels from the raw level 0 data in custom CDF format, the atmospheric excess phase estimates, that's our level 1B products, and then also the level 2 retrieved atmospheric profiles that contain the profiles of bending angle and temperature as a function of altitude. We also make available our secondary data, including navigation data. This includes the RINEX data, attitude data, and precise orbit determination estimates. The plot on the right highlights a comparison of our processing versus UCAR's processing, which is a standard processor of RO data. This is showing bending angle, mean and standard deviation statistics compared to CMWF. And you can see that for the most part, these statistics are quite similar to each other, with some differences in the lower troposphere due to the processing parameters that are applied. Next slide, please. Here I'd like to highlight some external evaluations of our data, which have been conducted over the last 5 or more years. This slide here shows 2 studies conducted in 2021. One of them shows that the penetration depth statistics of the Spire RO constellation is quite similar to the Cosmic 2 constellation, which highlights the quality of our data. The figures on the right highlight a study conducted by NASA that showed the introduction of Spire data in their assimilation model increased the overall impact of GNSS-RO measurements from 6th place to third place after the introduction of Spire data. Next slide, please. Similarly, on the European side, ECMWF conducted a study in 2020 during the onset of COVID, where it introduced Spire data into their model and found an increase in their FSOI, or impact on the model. This was during a time where a lot of aircraft with in situ weather measurements were grounded, and as a result, they needed another source of data to make up for that lack of measurements. So the introduction of Cosmic 2 earlier in 2020 with Spire data in mid-2020 allowed ECMWF to make up for much of that difference. The results on the right highlight more studies that compare the quality of Spire data versus Cosmic 2. So you can see these are highlighting bending angle differences from ECMWF for Cosmic 2 and Spire RO measurements. And you can see that the mean and standard deviation statistics are quite similar to each other, including the penetration depth of the signal. Next slide, please. Now I'm going to focus on polarimetric radio occultation, which is a newer capability of the Spire constellation. So polarimetric RO behaves similarly, or is similar to the RO technique. It's tracking the occulted GNSS signal, but instead of tracking the RHCP component of the signal, we're tracking the H and V linear polarization components. And by tracking these two different components, this has shown to have clear sensitivity to the precipitation along that signal path. So we launched the first of these PRO-capable satellites in January 2023. We launched 3 of them in total, and they were able to collect over 2,000 PRO profiles per day from all major GNSS constellations. To put that into context, that is 10 times the amount of data available from the PAS mission, which is the only government PRO satellite constellation or satellite in orbit right now. In addition to collecting measurements that are sensitive to precipitation, we can also use these measurements to derive traditional RO variables, such as temperature, water vapor. So we can think of these PRO measurements as enhanced RO, or it gives you an extra variable when compared to traditional RO technique. Next slide, please. Finally, I'd like to briefly summarize our ionospheric data collection capabilities. So for space weather, going back to the measurement configuration, we're tracking 1 Hertz measurement, 1 Hertz GNSS measurements through multiple antennas. These antennas, because they're tracked at dual frequency, can be used for the derivation of total electron content. In terms of data products that we provide provide level 0 raw data products, but also higher order processed data products, including TEC estimates, real-time simulation indices, which are they provide a measurement of the amount of signal fluctuation of the GNSS signal, and then finally electron density profiles, which are derived from our TEC measurements. Next slide, please. And finally, this slide summarizes some interesting space weather applications that have been conducted using our data through the NASA CSDA. The figures on the lower left here highlight an example of ionospheric wave detection or disturbance detected from our TEC data after the onset of the Hunga Tonga eruption in 2022. So the plot on the lower left shows the volcanic eruption in the Western Pacific. There's a tsunami front that's represented by the dark blue lines, and then the atmospheric wave front, which is highlighted by the cyan lines. And as our satellite is moving across this event, it's able to detect clear perturbations in our TEC signal, highlighted by the plot on the right. I also show some examples of thermospheric density estimates derived from our Spire POD estimates, that's shown on the upper right. And then also ionospheric electron density maps derived from our Spire data, shown by the figure on the bottom. You can see how for electron density, our coverage, because we're collecting at all latitudes, we're able to be complementary to the Cosmic 2 constellation, which is low latitude focused. So now I'm going to turn it over to Phil to cover GNSS reflectometry.
Thank you very much, Vu. So from that remote sensing of the atmosphere, we now move down to using the navigation signals for a different purpose, now looking at the reflections off the Earth's surface. So Spire has deployed a small constellation of satellites specialized for surface remote sensing using GNSS reflectometry. And this is using the same navigation signals as Vu was talking about in the radio occultation case, but now using the reflection from the Earth's surface as a form of bistatic radar. The reflection from each of the GNSS transmitters, whether GPS, Galileo, Beidou, or QZSS, contains a geophysical imprint of the surface. And so that information on the surface principally comes from the signal reflectivity. The roughness gives information on the ocean wind wave state. The dielectric properties give information on salt, moisture at the surface, and also surface inundation. And the scattering from covering volume can give information about biomass. And finally, the time delay gives information about surface height. Being an active system, the timing of the reflection gives selectivity of the location on the surface, and so we get a relatively fine spatial resolution, less than 1 kilometer, with the coherent reflections from smooth surfaces and around 20 kilometers on the incoherent scattering from rough surfaces. The history of GNSS-R datasets, I think, really starts with the collections from UK DMC, which was a UK satellite that collected short snippets of data lasting about 20 seconds in length. And then this was lengthened through on-orbit processing being introduced with UK TechDemoSat-1 that managed to really ramp up the duty cycle. And then this payload was incorporated into the NASA Cygnus constellation of 8 satellites that has a focus on tropical cyclones, but has as a byproduct, it's been found that it has a great deal of land surface applications as well. Spire came into this in 2019 with our first launch, miniaturizing the sensor down to the size of a 3U CubeSat. And we launched these satellites in small batches, maintaining the constellation at roughly the 2 to 5 satellite level. Next slide, please. So this is unlike the radio occultation phase-based measurement. GNSS-R observations need to be calibrated to the surface. So the key observable is the reflectivity, and that's the ratio of the reflection power to the instant power at the surface. But what we're measuring is at the satellite. So so we measure the reflection in the form of this here that we can see with a delay Doppler map, and some of the mapping of that power can give information about the surface, but also the reflectivity. And so we perform calibration to correct the reflectivity using the direct signal power, and the calibration is correcting for the receiver gain. And we use an active calibration system to compensate for any changes in the receiver gain and noise figure. And this is we took an innovative approach here that allows us to correct for the reflectivity, correct back to reflectivity without the transmitter power variations causing issues that had been seen on previous GNSS-R missions. And then the other corrections that are for the antenna gain pattern, the free space path losses and surface scattering area. And these let us get to calibration stabilities to better than 0.2 of a dB over several years. So if we go on to the next slide, please. So one of our key application focuses at Spire has been on the retrieval of surface soil moisture. So the surface reflectivity at L-band using these GNSS signals is sensitive to the dielectric properties, and Spire's surface soil moisture retrieval algorithm uses a semi-empirical change detection method. And that means we take the relative changes in reflectivity and we calibrate those using historical NASA SMAP observations to calibrate back to the surface soil moisture measurements to be in line with SMAP's measurements of centimeter cube per centimeter cubed in the top approximately 5 centimeters of the soil. So our level 2 product contains track-wise GNSS-R measurements of soil moisture. And the reason why GNSS-R is particularly interesting and complementary to other sensors is at L-band it can penetrate vegetation, but what's different is that it's an active sensor and uses forward scatter. And so this provides us high sensitivity to surface water. And when we compare to radiometers such as SMOS and SMAP, the technique is very complementary, providing correlation coefficients with SMAP up to 0.9, depending on the surface type. But where we are unique is the surface resolution. GNSS-R, due to the timing nature of the signal, provides a higher spatial resolution on the surface. So we can see that on the plots on the right here. GNSS-R has a footprint of 3 to 6 kilometers, whereas SMAP's native footprint is 36 kilometers. So we see on the top row soil moisture from Spire's GNSS-R sensors averaged over a dry period on the left and a wet period on the right. And you can see there's a lot more rich information on the spatial domain than can be seen in the SMAP's relatively smoothed measurements on the bottom row. So GNSS-R can provide robust temporal coverage though, because the precipitation information is a very fast changing signal. And so the use of small satellites gives information that can be have a much higher update rate than using the single exquisite satellites. So the other primary application that we're targeting is the same one as Cygnus, which is GNSS-R ocean wind wave conditions. And ocean wind is particularly impactful in operational weather forecasts and high impact weather events. And why is it that GNSS-R is targeted for this? Is because it can view the ocean in all precipitation conditions, and it can add rapid revisit of developing weather systems. So the ocean wind is retrieved from looking again at the reflectivity. Here we're looking at the normalized by static radar cross-section, and we perform a long track filtering to 25 kilometers. And we can also extract out the surface mean square slope. So we can see here on these plots the native measurement of sigma naught and how we retrieve wind and our comparison with a background from ECMWF forecast and also from analysis. And on the bottom of this slide, we can see the wind climatology represented in the scattering cross section and departures from ERA5 analysis. If we go to the next slide, please. So one of the other applications that we use on our surface observations is grazing angle GNSS-R using the spare capacity of our radio occultation satellites. So this can use the larger Spire Constellation of radio occultation satellites, and we measure the reflected signals at the end or at the beginning of the radio occultation event. And this is following the first grazing angle reflection seen on the CHAMP satellite in 2001. And what makes this type of measurement unique is that these smooth when reflecting off smooth surfaces, the reflections are coherent, and that enables carrier phase delay altimetry. So we process the observations at a high rate at 50 Hertz and use dual frequency to be able to correct for the ionosphere. And our Spire altimetry data can get down to within 16 centimeters RMSD height difference to the surface altitude models. Additionally, we retrieve the surface roughness and dielectric properties, and we output a number of products that we make available into CSDA, but there's a whole rich array of geophysical observables that we see in these data sets, which we think have got a great deal of scope for more use by the community and more exploration. Next slide, please. So one of the things that we love about working with NASA and through the CSDA program is it provides community of users that can take Spire data and validate it, find new use cases, and also help us to improve our products. And here I'm spotlighting one of the uses of this grazing angle data from Margaret Scott that was presented at IGARS this year on the Tonley Sap Lake. This is a lake which sees frequent cloud cover and surrounding dense mangrove forests. And so that makes it particularly difficult for being able to determine the geoid or the lake surface water height using ICESat-2 because of these difficult environmental factors to penetrate. So with grazing angle GNSS-R, being able to penetrate these environmental factors and having frequent revisits, it would be a great sensor to be able to use. So Margaret has got some results here that show some really similar results between GNSS-R, ICESat-2, and SWAT, with very good correlation coefficients and measuring within 7 centimeters of the ICESat-2 tracks. Next slide, please. So, as I was just saying, one of the things we love about working with NASA is that the number of different users that can look for new use cases. And so we've put together a few slides here, just a couple showing other uses that people have taken the Spire data through CSDA and either performed validation or found new use cases or helped us to improve our products. So Spire has a focus on operational commercial data provision, providing data to meteorological forecast centers for the medium range weather forecasts. NASA CSDA provides an ideal platform for community exploitation of our data and exploring new uses with observations that also provide a permanent climate record. And so we've put a selection of these community papers and uses of the data into this slide and the next that people can come back to for reference. So if we go to the next slide, and then the following part of the talk, I'm going to pass back over to Chris, who's going to talk about non-CSDA and also future Earth observation capabilities at Spire, which I think should be of interest to the community. So thanks very much.
Yeah, thanks a lot, Phil. So yeah, now, as Phil mentioned, I'll touch on Spire capabilities that are not part of the current CSDA program. The first is our maritime application, in which we're collecting shipborne VHF transmissions and tracking vessels that are broadcasting their AIS signal or automatic identification system messages. Many large vessels, such as passenger ships, fishing boats, hazardous cargo, tugboats, and other vessels are required to have an AIS transceiver, which then broadcasts a variety of data, such as a vessel's unique identification number, navigation status, ground speed, heading, dimensions, and numerous other static and dynamic vessel characteristics. What this slide is showing here is a heat map of a 60-day collection of AIS data. There's actually no base map. It's just the sheer number of data points that outline the land masses. Our satellite collections are in yellow, terrestrial collections are in green, and then the purple is a unique capability within Spire that we call Enhanced AIS. And this is where we have an exclusive partnership with around 4,000 or so commercial vessels in high traffic areas such as the South China Sea, Mediterranean, and Caribbean to host shipborne receivers. And the purpose of that is these receivers mitigate co-channel interference by collecting AIS transmissions within a certain radius of that vessel, and it'll increase the granularity of marine traffic that our satellites are able to receive in those areas by around 60%. Within our maritime suite, we also have the capability called Doppler geolocation validation, where we're using the Doppler effect of AIS transmissions to identify and geolocate vessels that are spoofing their GPS location and likely participating in some illegal activity, like illegal fishing, violating trade or oil embargoes, trafficking drugs, or any other illicit behavior. But every day we're seeing somewhere in the 1 to 400 vessels that are spoofing their GPS locations. And the common story is the vessel's transmissions will say it's on the western coast of Africa when it's actually transiting across the Atlantic to South America to likely conduct some kind of illegal behavior. Moving on to aviation, similar to the maritime side where we're tracking aircraft equipped with L-band ADS-B transponders or automatic dependent surveillance broadcast transponders. Our aircraft traveling in Class A, B, and C airspace within the US, and each country and international organization has their own qualifications of requirements for ADS-B transponders, but these messages include aircraft data such as position, identification, status, airspeed, altitude, and various other information. So we're collecting these messages to provide air domain awareness and predictive analytics for aircraft all over the globe. And this slide here shows a heat map of the 60-day collection of ADS-B data from both our satellite and terrestrial receivers. Onto our radio frequency geolocation. This slide provides an overview of the capabilities in that domain. We're able to task our satellites to collect over a certain area and center frequency or band to identify various emitters. And the table on the right here shows the numerous bands that we're able to collect, with VHF and UHF being primarily voice communications, several L-band to include GPS, GNSS, ADS-B, SATCOM systems, and then SX, KA, KU bands for several radars, including air defense and maritime radars, Wi-Fi signals, and more satellite communications as well. There are a variety of factors that influence the latency and accuracy of these collections, such as the frequency band, location of the collect, proximity to one of our ground stations, but really the goal here is less than 24 hours from tasking to geolocated output, and also less than 1 kilometer of accuracy. But a lot of the time, however, we're significantly faster and accurate down to tens and hundreds of meters in this regard. On the weather side, we also have our own team of meteorologists that are producing custom weather forecasts and observations for commercial and government customers. We're utilizing our own RF data from radio occultation and reflectometry that we just discussed, as well as other data sources to assimilate into our own model to provide single coordinate, regional, global forecasts on a 12-kilometer grid, and then current weather observations across the globe down to 3 kilometers or to a point or less. We're also able to provide over 30 years of reanalysis historical data and have numerous weather variable bundles such as maritime, thunderstorm, atmospheric, agricultural, solar energy, and several others that I'd be happy to share. Then moving on to a future capability, this is our, I mentioned earlier, our hyperspectral microwave sounder that's expected to launch next year. This is a joint venture with NOAA to develop the next generation weather sensor. Spire will be the first to fly an instrument of this type, and it's really expected to significantly improve numerical weather prediction. We expect to see greater accuracy and improved vertical resolution of atmospheric conditions when compared to traditional weather sensors. And the hyperspectral aspect of this payload is crucial for a couple reasons, with the first being that traditional passive microwave soundings, the presence of water vapor, rain, or ice particles could mix signals in some of the sensing channels. With hyperspectral sensing over 1,000 channels, we expect to be able to mitigate this effect, as well as the effects of RF interference from sources like GNSS jammers and 5G and future 6G broadcasts. And the reason for that interference is because 5G signals operate so closely to weather sensing channels that there's a real problem with the proliferation of cellular signals that could significantly and negatively impact the accuracy of current weather observation systems. So our HEMS instrument hopes to mitigate or eliminate that problem set altogether. And this is not part of CSDA, as I mentioned before. So we don't have our microwave technologies team on the call, but if anyone would like to discuss more about HEMS, can certainly feel free to reach out. I can certainly get you in touch. And then last capability that I'll touch on is our offering as a space as a service provider, which is where we'll integrate customer payloads into our bus and satellite system, whether it's hardware, software, or just an idea of a space-based application. Our engineers will work with the customer to develop a solution. Spire will contract the launch and operate the spacecraft while the customer receives the data from the payload. But our standard bus sizes are 3U up to 16U, but we're currently working on several projects for slightly larger spacecraft as well. We place a heavy emphasis on reliability, as all of our critical components and subsystems are TRL9, and there are several projects in the works that I can speak on. The first being our HEMS demonstrator with NOAA from the last slide. We're developing the next iteration of HEMS with the UK Space Agency, which will be similar in technology, but a larger payload with more power demand and increased capability. With the AFRL, Air Force Research Lab, we're on contract to develop a multispectral imaging cluster. With the NGA, we're participating in the MagQuest Challenge, and that's a satellite with a diamond magnetometer on an extendable boom, and it'll provide precision magnetic measurements to support the worldwide magnetic model. And then last project I'll mention is that we're working with the European Space Agency to develop an aircraft tracking constellation that will, in addition to our current ADS-B constellation, it will support air traffic management through the use of multilateration and being agnostic of ADS-B signals that may be spoofer jammed. So I mention all those just to show the wide variety of applications that can be performed from a CubeSat in low Earth orbit, and we're only looking to continue to expand our capabilities in that domain. So with that, again, thank you to everyone. I'll turn it back over to Jennifer for the Q&A portion of the webinar.
Well, thank you so much, Chris. We actually do have a couple of questions, but before we do that, what I'd like to do is open up the final optional polls. And let me do that really quickly so everybody can, and then we'll hop right in. Okay, so we've got our optional polls that are opened, and let me go ahead and jump into the Q&A. So the first question, everybody hear me okay? So the first question is perhaps a question for Dana to respond to, or Aaron. What is the distribution license for the RO data? My understanding is that NASA has purchased data with a restrictive license, which differs from the data from NASA missions, which are openly available to the scientific community. Are there difficulties in publishing scientific papers with the Spire dataset?
So I'll go ahead and take that one. So actually, the Spire data is purchased under a U.S. government EULA, which means anyone that is funded by the U.S. government or any one of our U.S. Government entities, academia that is funded by the U.S. government, tribal, local, state leadership, they can all access the data and use it. To publish results, you can certainly publish results, but you cannot re-disseminate the data publicly. So I think that's where the biggest restriction and difference is between the open science access of the NASA Earth science data versus our commercial purchase or acquired data, is just that dissemination mechanism.
Okay, thank you, Dana. So let's see here. Our next question, let me just check. I think the next question was actually in the chat. And the question is, are there any examples of successful elevation measurements for soil or vegetation?
It would probably be best if I take that. So altitude or elevation information over land should be something that's in the data sets, but whether the noise on those measurements is sufficiently low to be able to derive something useful, I'm not sure. I'm not sure whether people anyone has actually looked into that as an application. It sounds like it could well be a good opportunity. I know that using the same observable over, for example, ice shelves has been used as an altimetric observable, and that, as even just relying on the code phase or even incoherent scattering, being able to give ice sheet height to I think the about 1 meter level of comparison with other sensors. I don't think that the grazing angle approach that I talked about, which can do carrier phase altimetry, would work so much over these soil or vegetation examples, because in those cases I'd expect that the scattering to either be partially incoherent or have a large incoherent component, and that would make the retrieval of the carrier phase difficult to perform. So that would be why it would need to rely on the code phase measurements. So thank you very much. That is a great ask, and it may well be that someone who's been looking at in the community, and if someone has, then we'd love to hear about it.
Well, thank you very much, Philip. I just wanted to say really quickly something about the polls. I am opening this very same poll that will run out of time in a few seconds, the identical poll, a second time here after this, so you have an opportunity to respond to the short answer questions. Just taking a quick look at the Q&A, I don't see any additional questions at the moment. So while we are waiting on that, I just wanted to remind everybody that we did record this afternoon's event. And so if you have colleagues who were unable to attend today, they'll be able to take a look at this event and the recording offline. It's my intent to send both the links to the presentation slide decks as well as the recording link to all registrants within the next few days or so. So let me give this another look here to see if we've got anything. Perfect. Okay, so our next question is, the Spire satellite altitude has been dramatically lower to 200 to 300 kilometers, making the number of radio occultation profile decreasing. Is there a plan to launch new satellites?
Would you like to take this one for the RO future constellation plans?
Yeah, so I think, so over the last 12 months or so, a lot of our satellites have deorbited due to, as we enter solar max, we have higher thermospheric density, which increases our drag, and that has accelerated our satellite orbital decay rates. However, we do have several planned launches within the next 9 months. We had one in August that has replenished our numbers for a bit, and then we also have multiple launches upcoming that will introduce at least several on each launch that are capable of collecting RO measurements.
Okay, well, thank you so much, Vu. Let's see if we've got any additional questions. I'm going to hop back up to the chat just to see if there are any questions here. I do not think that I have missed any. Let's see. I don't see any additional questions. Let's see. So let's give it another minute or so. If anybody has any questions, please enter those into the Q&A. If you don't see that, you're welcome to also enter your question into the chat. And again, what we'll do if there are no further questions is we will leave the virtual meeting space open an additional 10 minutes from end time. And so if you think of something, you can feel free to add that feedback or query to the chat or the Q&A, and certainly we'll be able to follow up with our speakers offline. All right, any last questions from our attendees? All right, so let me just give it another look. And if not, let's see, what I would like to do, I don't see any further questions. So what I'd like to do is thank all of our speakers from Spire this afternoon, and also thank our speaker from the CSDA program. And let's see, our next CSDA vendor webinar will be held actually in January. There will not be an event held in December. And so be looking for that announcement on the Earth Data website at earthdata.nasa.gov. With that, any final comments from our Spire speakers or the CSDA program? And if not, we hope to see you at an upcoming webinar. Any final remarks? Okay. It looks like that's a no. So thanks so much, everybody, for taking time out of your day to join us this afternoon. And again, if you think of something, please feel free to enter that into the chat or the Q&A. And certainly we appreciate your feedback with the optional final polls. All right, well, with that, we will end this afternoon's CSDA vendor webinar with a focus on Spire, and we hope to see you at an upcoming event. All right, take care, everybody. Goodbye now.
Thank you.